In the last video, we talked about average velocity. That was section 1 from chapter 2. And at the very end, we briefly touched on this idea of a limit, of approaching a certain number. So this lesson is going to be all about limits and is going to give you a much better idea of what a limit actually is and explain it a lot better. So we're in the second section of chapter 2. We're going to be talking about limits of a function. And so at the top of your notes, we've got a definition. So the way that we would read this right here that's written in yellow, we would say the limit of f of x as x approaches a. So a is going to be some number that we're approaching. Could be positive number, negative number, fraction, whole number, whatever. So the limit of f of x as x approaches the value of a is equal to L. L just represents a number. That is always going to be a y value. So we have our x value down here. This is what we're going to get close to. And we're going to find out that our answer to a limit is a y value every time. So we've got the x value, and we want our answer to represent a y value. So what we're doing, and we're going to be doing this two different ways. We're going to be looking numerically in a table. We're also going to look graphically, so we're going to be able to see a graph, see a picture, and get a visual for what y value we are getting close to. Now right here it says the values of f of x get closer and closer to L, whatever this y value is, as x gets closer and closer to a. And we could be coming at this value right here from the left or from the right, so we can be coming from either side of a. But here it says that x is not equal to a. In other words, f of a doesn't actually have to exist for us to find the value of the limit. We can see what it's getting close to from the left. We can see what it's getting close to from the right, but the actual point, f of a, might not even exist. It might not. So let's look down here. It says consider the function f of x equals x squared minus 4 over x minus 2, and then back here it says that x cannot equal 2. Well, why can't x equal 2? Well, if you remember from both Algebra 2 and Pre-Cal, if we had this example, I'm going to take that numerator, it's a difference of squares, and I'm going to factor it into x minus 2 and x plus 2. And what do we see? We see that x minus 2 is a factor that's occurring in both the numerator and the denominator. So we would cancel those out, which indicate to us that there's a hole in the graph. Remember, we talked about rational functions, and we said that if a factor occurs in both the numerator and the denominator, it cancels out, and when that happens, there's a hole. So that's why our domain doesn't allow us to have x equaling 2. Not only that, but just going back even further to an easy definition, if we plugged in a 2, what would happen to the denominator? We would get 0, and we're not allowed to divide by 0, so there's a couple of reasons there, but that's why we have a hole. So what we would be left with is just f of x equals x plus 2. All right, so it says next, apply the definition of a limit to the function from above to find the limit as x approaches 2 of f of x. I've already got the numbers plugged in, so I've plugged in numbers coming that are to the left of 2, and I have numbers that are to the right of 2. So I plugged in some numbers on the left of 2 for x, I plugged in some numbers to the right of 2 for x, and these are the values that we see for the y values. Now notice we don't actually have a number right here, again, because x is not allowed to equal 2, because that's where there's a hole. But if you look at these numbers coming from the left side of 2, 3.5, 3.75, 3.9, you can see these numbers, they're getting close to 4. If we come at it from the right side of 2, the same thing is happening, that it's getting close to 4. So we would be able to say the limit of f of x as x approaches 2 is equal to 4. That's us finding the limit. That's us finding the y value that it's approaching. And we did that one numerically. We were able to do that from looking at a table. But if we go back to this and just talk about what that is, well, that's a linear function. We have a y-intercept of 2. we have a slope of 1. So if I were graphing this, my slope, I would go up 1, right 1. But remember, when I get to 2, there's a hole in the graph, doesn't really exist. So this would give us a linear function, but there is a hole there. We can see even in the graph, as we look at this graph and it approaches x equaling 2 from the left, we're getting closer and closer to a y value of 4. As we approach it from the right, we also are getting closer and closer to a y value of 4. So we get that same answer whether we use the table of values and look at it from a numerical perspective. We also get that same answer if we look at it from a graph. So we can tell the limit a couple of different ways. Now here it says, notice that the limit of f of x as x approaches a equals L in all 3 cases. Here we could get the same answer even though this graph looks a little bit different in all 3 of these pictures. In this first picture here, we clearly have a hole. Again, that numerator would be a difference of squares. The x minus 1 would occur in both the numerator and denominator. It would factor out. So we know that our domain says, hey, x is not allowed to equal 1. That's why there's a hole in this graph. Here, we now have a piecewise function. So this part represents this right here. This next part says, hey, if we plug in an x value of 1, we get out a y value of 1. That is the ordered pair 1, 1, which is what they have right here. But if I'm looking at what's going on from the left and what's going on from the right, I'm still going to get a y value for my limit of being 2. Even though there's a point occurring down here, but when I approach my graph from the left and from the right, that y value, even though it doesn't exist, is still going to be 2 for my limit. And then over here, we have the line, the hole has been filled in. We would get the same answer here as well. So we would have, coming from the left, coming from the right, we would still approach this y value of 2. So for all 3 of these pictures, even though they are all a little bit different, we would be able to say that the limit of f of x as x approaches positive 1 is equal to a y value of 2. Here, it didn't even exist. Here we had a hole, but we had a point down here, and here the hole was filled in. But they would all give us that same value. So whether or not the point exists or doesn't exist isn't the question. We are just trying to figure out what y value are we getting close to. So let's take a look at this next example. We have a piecewise function. So the first part says that when x is not allowed to equal 2, the y value is going to be 1. Now, if you just give a y value of 1, that's a horizontal line, right? That's just y equals 1. But it exists everywhere except when x is 2. So at the point 2, 1, I have a hole, but I get y values of 1 everywhere else. So what I've just graphed right there is the top part of this piecewise function. The bottom part of this piecewise function says simply when x is 2, we have a y value of 0. So we have an ordered pair of 2, 0. So there's the second part of our piecewise function. And so now it says use the graph to find the limit of g of x as x approaches 2. So we're looking for the y value. So we're going to come from the left of 2. We're going to come from the right of 2. And the y value that it's getting close to as it approaches that is right here at a y value of 1. So there's our answer for example number 1 using a graphic approach. Now sometimes when we do limits, we do what are called one-sided limits. We might just be interested in what's going on from the left, or we might just be interested in what's going on from the right. And so I know on this paper it's kind of hard to tell just because the font is small. But right here this says, okay, the limit of f of x as x approaches c, and then it has a little plus sign here. That means as x approaches c from the right. So I'm looking at this graph. Here's c. I'm going to approach it from the right side of the graph. That means I'm looking at this. And it's going to correspond with a y value of L for that particular picture. Now this next one is almost identical, except it has a minus sign instead of a plus sign. That means this time we are looking for a left-sided limit. So we're still going to be approaching the x value of c, but this time we're going to come at it from the left, which is going to put us at a y value of k. So our left-sided limit and our right-sided limit, sometimes they equal, sometimes they don't. It's going to depend on your picture. So let's see what's going to happen in example number 2. I don't know if I can I made that a little bit bigger. We'll try that. All right, so letter A, we're going to look at this graph. We want to approach x. We want x to approach 1, and we want to do it from the left. So here's 1, but we want to come at it from the left. That means we're going to be looking at this piece right here. We're coming at it from the left, and it corresponds with a y value of 3. All right, this next one, we're going to do the same number, but this time we want to come at it from the right side of 1. So we're going to look at this piece right here, and it is approaching a y value of 1. So those left and right, they didn't approach the same y value. The next one says we want to approach 2. Again, we're going to start off with the left. So here's 2. So we're going to use this piece. We're approaching the x value of 2. And the y value that it matches up with is going to be a 2. Here we want to approach it from the right side. So we're going to look at this piece right here. And when we get to an x value of 2, we are at a y value of 1. So those two also did not equal each other. The next one, we're going to approach 4 from the left and 4 from the right. So here's 4. If I approach it from the left, I end up right here at a y value of 2. And if I approach it from the right, I also end up at the same place at a y value of 2. So here we see an example of the left and the right sided limits actually did equal the same thing. In example number 3, we have a piecewise function. So let's graph it. So this first one, they're both linear. This one says that the first piece has a domain of x being greater than 2. I'm going to start by plugging a 2 in, knowing that that would be an open circle because I'm not actually allowed to include the 2. So if I plugged a 2 in, I would have 5 minus 2 times 2, which is 5 minus 4. So that's going to give me a 1. So I'm going to go to 2, 1 and put an open circle there. If I plug in a 3, 2 times 3 is 6. And then 5 minus 6 is -1. So I would have 3, -1. This time I have a closed circle because the 3 was a part of my domain. I can look and see that my slope is -2, so I could just go down 2 and over 1 to get to another point. And then I'm going to connect those. All right, so there's that first piece. The second piece, again, I'm going to start with a 2 and plug that in. So 3 times 2 is 6, and 6 plus 1 is 7. This one's going to be a closed circle because it does have that or equal to bar. So I'm going to go to 2, 7, which I've actually run out of room, but that's okay. I'm going to put it right up here with a closed circle. I see that my slope is 3. Now I'm not going to be going to the right because I don't want to go to the right. I want to go to the left. So I would just go down 3 and right 1. Or you could just continue to plug numbers in, and that would be okay as well, whichever way you want to do it. And there's my arrow. Now remember, anytime you do a piecewise function, your graph should pass the vertical line test. That's kind of a dead giveaway if you did your graph right or wrong, and it does pass the vertical line test. So we know that we've graphed it correctly. So we've done part A, graph it, we've done it. Now we're going to find out what the limit of f of x is as x approaches 2 from the right. So I'm going to use this piece. I'm approaching 2 from the right of 2, and I land at a y value of +1. Now we're going to do the same thing, but we're going to approach 2 from the left. So we're going to use this piece over here, which gives us a y value of +7. And then it says down here, what can you say about the limit of f of x as x approaches 2? Now notice it doesn't have the little minus sign or the little plus sign. So we know that we got one answer coming from the left, but we got a totally different answer coming from the right. And so what that means for us is, I'm going to write the letters D, N, E. That stands for does not exist. my limit does not exist because they are not both approaching the same y value. So if I want to find the limit as it approaches from both sides, it has to be the same thing in order to have an answer. And if I get two different answers, one from the left and one from the right, then I'm going to say that my limit does not exist. So that brings us to this next part. When do limits not exist? Well, if it approaches a different y value from the right as it does from the left, we just saw that in that last picture, we would get a DNE. If f of x increases or decreases without bound, so without bound would be like if it continues to go up for infinity, or if it continues to go down infinitely, then that would be an example of a does not exist, DNE limit. And then number 3 says if it oscillates between two fixed values as x approaches c. And we're going to see that in a graph in a minute, so I'm not going to really explain that yet until we get to the graph, because I think the graph does a great job of explaining number 3. So let's take a look at this example number 4. It says investigate using a graph and or table the existence of the following limits. So I've got some numbers here to plug in. Now we know that we actually cannot plug in a 0 because I would have a 0 in the denominator and I can't divide by 0. So I'm just going to scratch that one out. Now, if I plug this in, what happens to the absolute value of negative 0.5? It turns into positive 0.5, and then I'm going to divide by negative 0.5. So positive 0.5 divided by negative 0.5 is going to give me a negative 1. The same thing is going to happen with all of these numbers right here, because I'm going to turn the numerator into a positive, but then I'm going to divide by the opposite of that in the bottom. So all of these are going to be negative 1. Now over here I get to the positive numbers. What happens? Well, the absolute value of those positive numbers are still positive, but this time I'm also dividing by the exact same number. So a number divided by itself is going to turn into a positive 1. So what does that mean for my graph? Well, this part right here says that all of my y values are at a negative 1, and that's when my x values are all to the left of 0. So I'm going to have a horizontal line that looks like this. Again, I have an open circle here because I'm not allowed to include the 0. These numbers tell me that I'm going to have a y value of 1. So again, I'm going to have another horizontal line. But that's all going to be to the right of 0. So another open circle there because I can't include the 0. And I have another part of a horizontal line. So let's talk about the limit as it approaches 0. If I come at it from the left, I have a y value of negative 1. If I come at it from the right, I have a y value of positive 1, which we can see that in the graph. And because those two answers are different and not the same, that tells me that this limit does not exist. They have to be able to approach the same y values. All right, if we take a look at this next one, again, I've got some numbers in here for you. Now, if you remember this from Algebra 2 or Pre-Cal, that would be great as well. Remember, this is a rational function. My denominator, right away I know x is not allowed to equal 1. Now, in this case, it's not a whole. Remember, wholes only exist when you have a factor that occurs in both the top and bottom, and we don't have an x minus 1 in both the top and bottom. So what that does mean for us, if you remember, is that this is a vertical asymptote. So I already know that I've got a vertical asymptote right here. So we know that this doesn't exist because we're not allowed to equal 1. And if we plugged in these numbers here, and we could do that, so if I plugged in a 0, I would end up with a negative 1. If I plug in a 5/10, I get a negative 2. I'm just going to go ahead and fill these numbers in. And you could do this with your calculator or your brain. You know, I always suggest the brain power. But these are the numbers that we would get. So what's that look like? Well, so over here we've got 0, negative 1. We have a half, negative 2, half, hold on. No, I have that right. Okay, sorry. Half, comma, -2. I can tell it's still summertime because my brain is not all there. 0.9. So we're going down pretty quickly. So it's going to be going something like this, right? And then these numbers over here, we've got 1.5, comma 2, we had 2, comma 1, kind of like the opposite, right? It's going to look something like that. So what's happening as it approaches x from the left? Well, it's going down infinitely. What happens as we approach the 1 from the right? It's going up without bound. So remember number 2 on the list of when is it D and E? When it goes without bound, we have 1 going towards positive infinity, we have 1 going towards negative infinity. So for us, that's going to be another example of does not exist. Now let's take a look at this last one, or not the last one, the next one. If I look right here, and I've plugged in some kind of odd looking things, right? So I've got 2 over pi, 2 over 3 pi, 2 over 5 pi. If we were to plug those in, so right here, if I did sine of 1 over 2 over pi, that would turn into, we would change that into 1 times pi over 2. So really that would just be sine of pi over 2. And if you remember from the unit circle or the way that the graph looks, that's going to give us a y value of 1, which means this would turn into sine of 3 pi over 2, which is -1. And then it would be sine of 5 pi over 2, which is 1, and sine of 7 pi over 2, which is -1. And you probably can see the pattern here of what's going on. Now right here, there's supposed to be an arrow on this paper. I'm not really sure why there wasn't, but anyways, here we go. Now let me tell you that this is kind of weird, right? The y value, so we've got +1, -1, +1, -1. And we could check this out in our calculator. So let's try that real quick. First of all, you want to make sure that you're in radians, which I'm glad I checked because I was not in radians. Anytime you're dealing with trig, we want to be in radians. And so we're doing sine of 1 over x. And then when I graph this, I'm going to go to the zoom button real quick. I'm going to go to number 7 where it says zoom trig because we want to use a trig graph as opposed to like a regular 10 by 10. So I'm going to just hit the number 7. And I'm watching it graph right now. You saw it kind of in the middle. It kind of did some funky things, but what did it do? Well, I'm going to zoom in and see exactly what it did. So I'm going to hit zoom. I'm going to go to number 2, zoom in. And you probably see the blinking cursor. You can decide where you want to zoom in. I kind of like where it already is right here at the origin. So I'm just going to hit enter and we're going to see, watch what happens. See, it's kind of going up and down and up and down and up and down from -1 to +1, -1, +1, -1 to +1. That's what it means, that number 3, when it says it's oscillating between 2 fixed values. Our graph is oscillating between the -1 and the +1. So it's kind of like, I'm going to say this right here is 1, and this down here was -1. What we just saw happening in the graph is it did something like this, up and down and up and down and up and down and up and down, and then it kind of goes back to looking like that. So as I'm approaching 0, what's happening? It just is up and down, up and down, up and down, up and down. And so this is another example of D and E because it's oscillating between those 2 fixed values of -1 and +1. So those are the times when we get a D and E. Now we talked about vertical asymptotes a few minutes ago. We refreshed our memory a little bit from Algebra 2 and Pre-Cal. Let's approach that from a calculus perspective. We get vertical asymptotes anytime you have a limit value of either a positive infinity or negative infinity. Now it could be that way coming from just the left or just the right, or maybe both sides. Same thing here, we could approach this negative infinity coming from the left, coming from the right, or if it's both, just coming at it from both sides. But anytime, whether you have a one-sided limit or just the limit from both sides, if you get a negative infinity or a positive infinity, which is at D and E, okay, because it's unbounded, so it's either going up forever or going down forever, that always indicates that we have an asymptote. So let's take a look down here. Now we know how to do these types of problems, but for this one, it wouldn't factor so much for us like how we're used to finding the asymptotes. So let's take it from a numerical perspective. I'm going to plug in, I'm going to plug in some random numbers. So I'm going to do like 0.9, 0.5, 0, -1, and -2. This is my approaching the 1 from the left. And then I'm going to do a table where I'm going to approach the 1 from the right. So 1.1, 1.5, 2, 3, and 4, just making up some numbers. So we could take the time to go through and punch all of this into your calculator. I'm gonna shorten that up for us because this video is gonna be kind of long anyway. So I get a -7.1, then I get a 0.5, then a 1, then another 0.5 again, and then a -1/3 or maybe -0.3 repeating, however you want to put that on there. And then over here, I've got, with the 1.1, I have a 13.1, a 5.5, a 5, another 5.5, and then a 6 1/3 or 6.3 repeating. So the first one says, okay, what's the limit as we approach +1 from the left, which is this first table right here. Well, look at the numbers, right? It shot down pretty quickly. So this is telling me it's gonna go down quickly, and it's gonna go down to -infinity. If I look at it from the right, and I'm looking at these y values, what are they approaching as we get closer to an x value of 1? These shot up pretty quickly. This is gonna approach +infinity, which again means that my limit doesn't exist. But what else does that mean for us? Well, because it approached either a -infinity or +infinity, according to calculus, this tells me that we're going to have a vertical asymptote when we have an x value of 1. So now we know another way to find vertical asymptotes coming from a calculus perspective. All right, let's take a look at this next one here. We're going to investigate this limit. This is actually a special one, so I would put a star beside it. All right, we're going to be investigating this using the table and the graph. I'm going to plug in, we were trying to get towards 0, so I'm going to start with some small trig numbers. I'm going to do a pi/8, that's a small one, then pi/4, pi/2, pi, and then 3pi/2. And then I'm going to go, these are all from the right side of 0. And then I'm going to do the left side of 0. So really that just means I'm going to use the same numbers, but I'm going to use negatives. So I'm going to have a -pi/8, -pi/4, blah, blah, blah. I think you'll get the gist. All right, so we're going to take those and we're going to plug them in. Now I would definitely, if you're doing this on your own, I would definitely use a calculator. So here's what I got when I did this. I got 0.974. And then the next one I got 0.900. Obviously I'm rounding these. And then I got 0.637. And then at pi I got just a 0. And then at 3pi/2 I got -0.212. And then plugging in those negative ones actually got me the same exact y values. So then the 0.974, 0.900, 0.637, a 0, and then a -0.212. Now you'll notice I didn't plug in a 0. Again, why am I not plugging in a 0? Well, then I have a 0 in my denominator and I'm not allowed to have that. So let's see what's going on. So I'm gonna say, I'm gonna make this right here pi/2. All right, which means halfway there, this would be pi/4, which means half of that would be pi/8. All right, if this is pi/2 and I had gone 2 spaces over to get that, Then I would go another 2 spaces over to get pi, and then I would go another 2 spaces over to get the 3 pi over 2. So I'm going to go ahead and do the right side of 0 and then just mirror it over, since everything, all the y values are the same for the left side of 0. So at pi over 8, I'm almost at 1. Now I'm going to put my 1 just up here, just so we kind of get a better idea. So I'm almost at 1. And then at pi over 4, again, I'm getting pretty close to 1. And then at pi over 2, I'm moving down some, right? And then at pi, I'm at 0. And then I go below the x-axis here once I'm at 3 pi over 2. So I get something that looks like this, all right? And the same thing is going to happen on the other side. I'm going to get something that looks like that, okay? But remember, I'm not allowed to have anything when x equals 0 because that can't be a part of my domain. So I'm going to be putting a hole right here because it doesn't exist. So the question to this then is, what's the limit as I approach 0 from the left and as I approach 0 from the right? What y value did it get close to? Got close to 1. This right here is going to be a pretty important one that we see. And so that's one that you're going to want to memorize. So anytime you have the limit when x approaches 0 of sine x over x, it's always going to equal 1. That'll come in handy for us, and you'll see that in the upcoming weeks. Just keep that one in mind. Keep your star beside it. Highlight it, whatever you want to do. Just know you need to know that one. All right, so let's practice some of this down here where we're interpreting whether or not these things are true or false, depending on our knowledge of the one-sided limits and whatnot. So this first one says, the limit as we approach -1 from the right is equal to 1. So here we go, approaching -1 from the right. Does our y value equal 1? Absolutely. So that one is true. All right, letter B, it says the limit of f of x as we approach 2 does not exist. Well, in order for it to not exist, remember those 3 things that we learned, but one of the main ones that you always look for is, do the left and the right-sided limits, are they the same or are they not? So if I approach 2 from the left and I approach 2 from the right, are they approaching the same y value? Absolutely, they're both approaching a y value of 1, which means the limit does in fact exist. So this one right here, this is false. It would not be a D&E problem because they both are approaching a y value of +1, whether we come from the left or come from the right. All right, the next one says the limit of f of x as x approaches 2 is 2. Well, we just saw, talking about this last one, the limit as we approach it from the left and approach it from the right is actually a y value of 1. So this one's also false. All right, the next one says the limit as we approach 1 from the left is equal to 2. So we're going to look at this piece right here. And as we approach 1 from the left, are we approaching a y value of 2? Absolutely. So that one is true. All right, letter C, we're going to approach 1 from the right, and it says that our limit is 1. So we're going to look at this piece right here. We're approaching 1 from the right, and yes, it is approaching a y value of 1. So this one is true. All right, letter F, it says we're going to approach 1. So that means from both the left and the right, and it says does not exist. So as we approach it from the left, we get a y value of 2. As we approach it from the right, we get a y value of 1. And because those are different, yeah, this is a D&E. So it does not exist. All right, this next one says that the limit as we approach 0 from the right is going to equal the same thing as we approach 0 from the left. So if I approach 0 from the right and I approach 0 from the left, are we approaching the same y value? Yes. So this one's true. They do equal each other. All right, this next one says the limit of f of x as x approaches c, so that could be any number on here, for this domain. It says it exists at every value of c between -1 and +1. So whether or not it's 0.9 or -3/4 or 0, just any number between -1 and +1, would the left and the right sided limits be the same? And as we're looking at this, whether you're coming from the left or the right, for all of these pieces in between -1 and 1, yeah, they would absolutely be the same. So this is true. And then this last one for this example says the same thing, but gives us a different domain. So we're looking from 1 to 3. So whether we're approaching these numbers from the left or to the right, anywhere between 1 and 3, do they all have the same values? Yeah, they sure do. And so that would also be true. All right, so what I would like for you to do is you do those on your own, and then you can check the answers along with what I've done when you look at the notes. So I'm not going to go through that with you. I want you to try that. The last two examples are kind of just applying what we've learned and seeing if we could draw a graph. Now, with these types of problems, there's more than one correct answer. We just need to make sure that whatever it is that you draw lines up with this information right here. So it says sketch the graph of a function with the given limits. So I'm just going to real quick draw x and y axes. All right, we're going to be approaching x at -3. We're going to be approaching x at 2 from the right, and we're going to be approaching 2 from the left. So I'm just going to do this for my graph. All right, so this first one says that as x approaches -3, we're going to be approaching y values of 1. Now notice it doesn't have either the little plus or the little minus. That means that both have to be the same. So I know that I need to be approaching a y value of 1. I could maybe do something like this. So here's my -3. If I approach it from the left, if I approach it from the right, both of those are giving us a y value of 1. So that could be something I could do. You could even put a hole here and then put a random point someplace else, and that would be okay, because even approaching it from the left and approaching it from the right, we would still have a y value of +1. So you have a couple of options for what you could do there. Now we want to continue this graph. We want to approach 2 from the right and 2 from the left. Now let's do the left first, because that's what we would get to first, right? That's because I'm going from left to right. So from the left, I need to get a y value of -1. So I'm getting to 2. I need to have it approaching a y value of -1. So maybe I take this guy and I do something like this. So I have from the left, I'm approaching a y value of -1. But from the right, I want to approach a y value of 4. So maybe this side of the graph could look something like this. As I approach it from the right side, I'm getting a y value of 4. So that could be a graph that would work for that type of problem. Like I said, there's lots of answers that could work. You just need to make sure that whatever you graph, all 3 of those conditions have been met. And so let's try one more together. And this is the last one. And this one is dealing with positive and negative infinities. All right, so our x values that we're going to approach, we're going to be approaching -2, both from the left and the right. And we're going to be approaching +4. All right, so let's talk about the -2 first. We're going to approach -2. When we do it from the left, we want to be going to negative infinity. So we want our graph to go down. I changed this. I'm sorry. It was a -3 on the paper. We're changing it to positive infinity. So from the right, we want to be going up. From the left, we want to be going down. Well, what does that mean for us? Well, that means there's definitely been a vertical asymptote there. And so from the left side of the graph, we're going down from the left side of -2. From the right side of -2, we're going up. So we're going up towards positive infinity. Now let's talk about what's going on over here when x is 4. We want to be going up. Notice it doesn't have the little plus or the minus sign. That means on both sides of 4, we want to be going up. So, got another vertical asymptote here. Going up over here and over here on the other side, on the right, I'm also going up. And so that would be a good example of what we could draw for example number 12. All right, so make sure that you do example number 10 on your own. Try that one out, and then you can check the notes and see if your answers match my answers.